first product we're going to see is called perpetual American call. We're also going to look at perpetual American put as well. Now, for a perpetual American call, it provides this typical call payoff, which is a max of S minus K or 0. Now, being American, this call can be exercised at any point in time. So once it's been exercised, and this will be the payoff. Now, why are we talking about perpetual American call? Can we talk about perpetual European call? Well, the answer is actually no, because for a perpetual European call, the value is 0, because for a European call, you can't really exercise any point in time you want it. You can only exercise a maturity, and in this case, the maturity is infinitely far from the present time, so you will actually never get to exercise. So this thing has absolutely no value because you never get any payoff. So only for when we talk about perpetual products, in this case, only perpetual American call and a perpetual American put makes sense. European products, perpetual European products doesn't really make sense at all. For a call on a non-dividend paying stocks, we have said that in that case, if we have an American call on a stock that does not pay any dividend, then that call should never be exercised before the maturity date. So although the American call gives the holder the right to exercise any point in time before maturity, in fact, if it's American call on a non-dividend paying stock, it's never optimal to exercise that call before maturity. And also we said that in this case, the European call and American call, they have the same price. Now, if it is a perpetual American call on a non-dividend paying stock, does it really mean that the European call and the American call has the same price? And also that we have seen earlier that a European perpetual call will have no value, 0 value. Does it really mean the American call, in this case, will also have 0 value? Well, the answer is obviously no. But what's the reason? So let's keep those questions in mind, and let's look at how we can price a perpetual American call. And through that process, the question that we've just asked will be answered. Now, although for the perpetual American call, the option is perpetual, one may think that there may be certain conditions where it's optimal to exercise. Suppose we have those conditions. And what are those conditions that we must have? What are characteristics of the condition? Well, the characteristic of the condition must be that if we were to have a condition then at a particular time, then it must be the case that if we were to exercise at that point in time, we'll have a value greater than any other time after this t that we exercise. So every time we exercise, we'll have S minus K. So if we were to have the condition satisfied at the time t, it must mean that S minus K at time t will be greater than any other S minus T at time at some other big T greater than this small t, okay? And we probably cannot say that it will always be the true case, that we would never have any, but in a risk neutral world, we should have that any other expected value at S minus K at a later time would never be higher than the exercise value. So the expected value will be the value of waiting. Expected value of this payoff at any point in the future is the time of waiting. It is the value of waiting or not to exercise. But here is the value of exercising at time t. So we will say that the condition must be the case that the value of exercising immediately is higher than the value of waiting. So let's see how we derive that. Now, if we have a stock, the underlying stock that follows a log normal process and has a dividend yield of Q, we know that we have a fundamental pricing differential equation of this particular form that we have seen earlier. Now, suppose there is some level H for the stock S. If the stock price reaches H, then it's optimal to exercise. We don't know what H is. That's what we try to derive what H means. But suppose there is an H, and H being the optimal exercise level, that must mean that as soon as the stock price reaches H, we should exercise. Okay. Now, if we have this, then the boundary conditions are H minus K, H being the optimal level of S that we have to exercise. So H minus K will be the payoff. Okay. Now, if S gets to 0, obviously the value of the perpetual American call will be 0. Okay. So the other condition is that we have the boundary condition. So F is equal to this when S is equal to H. What happens when S initially has to be less than H? So S is moving up towards H. So if S is actually greater than H to begin with, then we would have already exercised that. Okay, so then the value, if S is greater than H, the value of the asset should already be S minus K, S minus K by design. So the condition only makes sense when S is less than H to begin with, and then approach H. So as soon as it crosses H, we should exercise. If it never crosses H and it reaches 0, then the value will be 0. Okay. Now suppose we have this magical level H, and we say that now just by looking at the partial differential equations, we know that for a given level of H, that partial differential equation does have a solution. So that solution here satisfies the PDE and the boundary conditions. Okay. Now, and so this basically is a solution of this PDE. Let's take a look at why it is. And in this case, alpha must equal to this, and then with W, then it's equal to that. So we're claiming this is a solution. We have to show that it is indeed a solution. So let's take a look at it. So if this is the solution, then the solution must solve this, right? So what's df dt? It's not a function of t, so df dt is 0. It is a function of s, so df ds has this particular expression here, and which is really, if you simplify that, it just alpha divided by S times F, okay? And the second partial, if you derive that, is really just alpha times alpha minus 1 divided by S squared times F. So if you put those partial derivatives inside into the equation becomes this, okay, after substitution. Now you can drop the F's here, so they're on both sides, and rearrange. You will have a condition like this. And if you do that, and you can then solve what is for A, right? Oh, sorry, this alpha here. And so alpha will be this thing, and W is just this. So this is just a shorter way of writing the alpha out with this variable W defined it as this, okay? And alpha should be greater than 0, okay? So we see that if alpha is having this particular condition, then indeed this is the solution of this partial differential equation, okay? Now, okay, we have this being the solution, but it still doesn't tell us what is the right level of H is. H now, the solution or the price is now a function of H, but we cannot get the actual price unless we know what the optimal H must be. So what value does H take? Now, to get the optimal level of H, it must be the H that maximizes the value, okay? So we have to take a particular value of H that maximize the value F. So how do we do that? Let's just take a look at the chain df/dh, and we do an optimization there. So take the derivative here, set it to 0. What do we have? We have this particular H star has an expression of K times alpha divided by alpha minus 1. Okay, now we have to show that this is actually indeed a maximum rather than a minimum. Now, obviously, you can check this is actually the maximum by looking at the second derivatives to see whether it has the right sign. Okay, and then we verify that this is actually, you can do that to verify this is actually the maximum. And if this is the case, your H must take this particular form, then substitute it into this solution here. So where you will have the value of the perpetual American call with an optimal H level like this, and this particular solution satisfy the fundamental partial differential equation, so this must be the solution of the call. So you plug that in, and after some arrangements, which I've shown here color-coded, eventually you get an expression like this. Okay, and you know that this must be the case where S is less than H. Okay, because there's no point of looking at S is greater than H. by definition, by design. So now everything is in parameters that we know. We know K, we actually know alpha. Alpha is actually in terms of things we know. In terms of R, in terms of Q, in terms of sigma, we all know them by design. So then essentially this will become the solution of the perpetual American call. Now, once you're armed with this solution, we should go back and ask that question. The question is that, didn't we say American calls should never be exercised? Well, it shouldn't, it's not should never be exercised before. It's only never exercised before maturity when the underlying asset does not pay dividend, okay? So does this solution give that to us as well? Well, if American, let's see if American perpetual American call, and let's say the underlying asset pays no dividend. So in that case, Q will be 0, and our W term will then be just R minus sigma squared divided by 2. Then if you have that, you plug in a W term like this, you'll find that alpha is equal to 1. And when alpha is equal to 1, what's your optimal level of stock price to exercise? Well, the optimal level of stock to exercise will be infinity. So that means anytime for any finite value of stock, you shouldn't really exercise because it doesn't cross that boundary. So when you have a American perpetual American call, where on a stock that pays no dividend, indeed, the optimal solution here tells us that you should never really exercise that. Now, in this case, if you don't exercise, doesn't really mean it doesn't have value, because you can exercise it. It's just if you wait, you get better value if you wait. So your waiting value is better than exercising value. This is actually different from holding a European call in this case, because European call does not allow you to exercise. And therefore you will never be able to receive a payoff. But for American call, you can always exercise, although it is probably not optimal in this case to do, because you may have better value. But because you can exercise, that's why it has positive value. It's not 0. And when we say it's not optimal to exercise, that means you're better off selling this American call, this perpetual American call, than to just go exercise it. So you give it to somebody who is willing to wait, and that person will hold this American call and pay you more than you would otherwise go exercise it, okay? So that reconcile with what we have just discussed earlier. So there's no inconsistency here, and the analysis check out.